right. I guess we're live, right? So good morning, everybody. I'm Dave Landsman, the Director of Industry Standards for Western Digital. I hope you all got to listen to the talks in the DNA data storage track yesterday. If not, they are available on the SDC website for viewing and download. So please make sure to go check those out. You can get slides and videos. So today we're closing the DNA storage track with a panel of representatives from the DNA Data Storage Alliance. Our track is entitled DNA Data Storage, Preserving Our Digital Legacy. The Alliance, DNA Data Storage Alliance, was formed in November 2020 and now has nearly 40 members. Our goal is to facilitate the development of DNA data storage as a complement to existing storage solutions. This is really critical because the amount of digitized information being created today is outpacing the ability of existing storage systems to store it. So this trend, if it continues, will force us to throw away raw data, which, if saved and mined, could literally become tomorrow's new knowledge. A brief word about the technology we're talking about here. Though storing bits by using electric charge, magnetic moment, or resistivity in inorganic material has become kind of an everyday miracle for those of us in the tech industry, DNA takes data storage into an entirely new realm. We must now consider how molecules behave in fluids, such as how fast they move, how physically long they can get, how to preserve them, and how to embed them with metadata, error detection and correction codes, and other information needed for reliable transmission. And finally, we must integrate the wet lab part of all this technology with semiconductors to automate and scale to an end-to-end storage system. It has been, I just have to say, it's been a pure delight to begin learning about all this technology and meeting some of the distinguished technologists and scientists within it. I hope all of you watching will get as excited as I have, and also get involved with the DNA Data Storage Alliance. Lastly, I'd like to offer a big thank you to SNIA for hosting this track at SDC. And I'm now going to turn the floor over to John Hoffman, lead scientist at Quantitative Scientific Solutions, where he manages advanced research and development programs in molecular information storage. So take it away, John.
Great, thanks Dave for the introduction. And I'd like to second Dave, and on behalf of the panelists, thank SNIA for providing this forum to introduce the DNA Data Storage Alliance and discuss the emerging field of DNA data storage. The panelists and I would like this to be an interactive discussion, and we encourage the audience to post questions in the Q&A feature within Zoom. I'll be monitoring both the Q&A and the keynote session Slack channel, and will pose your questions to the panelists. If you'd like to continue the conversation after the panel discussion, please use the DNA Data Storage Slack channel. So I'd like to start by briefly introducing the DNA Data Storage Alliance and our panelists. The DNA Data Storage Alliance was founded in October 2020 and is now composed of nearly 40 organizations with the mission to create and promote an interoperable storage ecosystem based on DNA as a data storage medium. The organization's scope covers market education, developing use cases and industrial roadmaps, and recommending which use cases warrant the creation of standards and specifications. We'll hopefully discuss many of these topics today, but I recommend you visit dnastoragealliance.org for more information. I'd next like to introduce our panelists who represent the 4 founding members of the DNA Data Storage Alliance. I'll begin by introducing Dr. Karen Strauss. Karen is the Senior Principal Research Manager at Microsoft Corporation and an affiliate professor at the University of Washington, where she co-leads the Molecular Information System Laboratory with Dr. Luis Ceze. Our next panelist is Dr. Craig Chesla. Craig is currently the Vice President of Advanced Engineering in the Research and Technology Development Group at Illumina. Next, I'd like to introduce Daniel Chosh. Daniel is the Senior Director of DNA Data Storage at Twist Bioscience, and since late 2019 is leading the commercial side of Twist's DNA data storage product. And last but not least, our final panelist is Stefan Helmold. Stefan is currently the Vice President of Strategic Initiatives at Western Digital. Okay, so I'd like to start the discussion with a question for Stefan. Stefan, I'm hoping you can expand on Dave's intro. Why do we need new data storage technologies? What are the challenges the storage industry is facing, and where does DNA data storage fit in?
Yes, good morning, everyone. And if you can advance to the next slide, John, I'll be happy to go and provide, first of all, the why do we need DNA data storage? As we're looking into the growth of data, there is no stopping, so it seems. And we just wrapped our brains around how we manage data lakes and how we not only store them, but also how we basically process them. And next, we get to think about how we scale those data lakes up to data oceans. And there's one thing that seems to be for sure based on projected demand. The experts estimate that the supply of data storage won't keep up with the demand. To give you an order of magnitude of impression here of growth, we have a chart here that is providing a number of scenarios provided by Gartner, how much data storage may grow over this decade, right? The nominal scenario is at about a 15x growth, 15x growth. And when you go all the way up to the highest scenario, we may see as much as 50x growth over where we are today when you look at the data storage required within the data center. That gives you a flavor of what scaling would be required of storage solutions in order to keep up with that demand. The Semiconductor Research Corporation has set a goal of growth for areal density capability for memory as well as storage to the tune of 100x or more from where we are today. Now, looking at existing storage technologies that are serving the majority of bits today, such as hard disk drives and SSDs, we can clearly see that we may get an order of magnitude scaling out of those, maybe a little more than that, but certainly not 2 orders of magnitude scaling. And it turns out that DNA data storage is actually the only technology candidate that holds promise to deliver on that scaling target of 2 orders of magnitude or more of areal density capability growth. And again, as mentioned, when you look at the data center overall, not only do you need to store the data, but you need to have a means also to compute the data, and not only hot, but also cold data. And for that, yet again, the unique characteristics of DNA data storage make it an ideal fit for storing and for processing data.
Great, thanks, Stefan. In some of the conversations I've had on this topic, I've heard that when dealing with these exabyte scale or data ocean type archives, that archive replication is also a challenge with existing technologies. And this would be in support of use cases that require, for example, multiple geographically distinct copies of an archive. Do you agree that's also a challenge?
Yes. Part of the challenge here is that the replication, right, is done in order to have resiliency if you lose a copy, right, so that you have other copies and you never lose data, right? That's why we're doing this, right? And again, the nice thing about DNA data storage is because of the unique characteristics that it has, it is very easy to make copies. And you could physically distribute them in multiple locations, right, in order to have that replication goal. And it comes at little to no cost in case of DNA data storage to replicate the data.
Great, thanks, Stefan. So kind of building on that, I was hoping Karen could take the next question. So Karen, given these challenges that Stefan's just discussed, why do you think DNA data storage is a potential solution? And what makes data storage special as a storage media? And more, and a follow-on is what are the limitations?
Yeah, so Stefan already pointed to some of the benefits of DNA data storage, right? So density is quite high compared to other types of media. It will also can be made to last for quite a while, for a long time. We're talking about hundreds, thousands of years. And there's demonstration even in the wild that DNA under the right conditions will last for a while longer. This is good because essentially as the technology improves, we don't need to be copying to new types of media. The medium is stable and lasts for a long time, and we don't need to migrate to the next generation storage to get the benefits of the high density. In addition to that, now that we have the technology to read DNA, be it biological or not, we'll always have the readers to recover digital data that's stored in DNA. So from a relevance point of view, we can keep it in DNA for a while. So it's not like floppy drives or anything like that, where we lost the ability because they're no longer readers. And finally, from a sustainability point of view, DNA, based on preliminary work that we did, requires quite a very little material to store the information, and also carbon emissions are lower, energy consumed and water consumed compared to other media. Seems quite promising. Obviously there's a lot of assumptions there, but the technology does look promising. Now, in terms of limitations, there's quite a bit of improvement that's still needed. And, I'm confident that among the almost 40 companies that we have in the DNA Data Storage Alliance, we're going to, make many improvements on DNA data storage. But a few to highlight are higher read and write throughput. There's quite a bit of improvement that's needed there. Also lower cost, but those two, the throughput and the cost, are tightly related. So I'm pretty optimistic about that. And another limitation is higher latency. And that's why we think archival storage is probably the first place for DNA data storage to go into. But I'm looking forward to innovation in this area as well. So I think I'll stop there.
Great, thanks, Karen. I appreciate it. So my next question is for Daniel. Daniel, I'm hoping you can provide an overview of how DNA data storage is done today and discuss how Twist is approaching the process. And I've got a slide here that might help us talk through it.
Yeah, great question, John. And I also would like to add to Karen's answer before on the limitations that we need to, as an industry, need to grow up from the individual devices that we use today to build an automated kind of a solution like the storage industry is needing. The storage industry is used to get like a solution that plugs and play into the data center and plays well with other storage technologies, and we will need to also invest in that part. Now, regarding how DNA data storage is done today, so basically you can see here we have 6 main steps. The first step is we take the digital data. We basically take any file or any object that is basically zeros and ones in the behind the scenes, and we translate that into AGCNT. We're using a codec that can be developed by any member or any company or any individual can develop a codec. We develop our own, and then we translate it into AGCNT. This is still on the digital realm. We have now a file of a long string of AGCNT, and then our codec also breaks up this long string, because currently DNA synthesis is not able to synthesize the huge strings of AGCNT. So we break it down into small chunks. They're called oligos. And on each oligo, we put some data, and we put some error correction data, and we put some metadata and indexing data. And then we move to the second step. The second step is the synthesis part, where we make the actual DNA. This is where the digital moves into the physical world. Twist has developed highly efficient and high throughput DNA printers. It's called a synthesizer that is able to print the DNA. Once we print the DNA, we put it in tubes and then encapsulate it in special capsules. If you guys heard the talk from yesterday from Mart, from Imogen, you can hear more about this technology. Between step 3 and step 4, there can be hundreds of years or thousands of years once we want to read the data. In step 4, we open those capsules and we take the DNA out. On step 5, we're doing a process called sequencing. This is the process that takes us back into the digital world. It takes the physical samples of the DNA we produced using a process called sequencing. If you heard Craig's talk yesterday, you can also access it in the agenda webpage on how it is done to read back the DNA from the physical form to the digital one. And then we put that digital file that is back into the AGCNT into the codec for the decoding process that will take it back into ones and zeros and will build a file as it was in the beginning, using all the error correction data in case there are some errors in the synthesis or in the sequencing. And Twist today is doing all those steps. We're doing a few projects. If you'll see in our website, we have some examples. And basically, we're doing now projects that are doing end-to-end of files that people want to put in DNA.
Great, thanks, Daniel. Yeah, there are some questions in the chat that I think address some of the points that you just raised, or your points address the questions in the chat. But I'll move on quickly for a question for Craig before I move in there. Craig, I'm hoping you can discuss how the life sciences industry has supported or enabled DNA data storage technologies, and maybe talk a little bit about how DNA data storage requirements are different than those for life sciences applications.
Sure. Yeah. Thanks, John, and thanks for the opportunity to SNIA for us to have this panel today and the session on DNA data storage. So the life sciences industry, there's been tremendous amount of innovation over the last decade plus on both the sequencing and synthesis steps that Daniel just explained. Specifically for Illumina, where I work, we've made tremendous progress in reducing both the time it takes to get from the retrieval step to the decoding step. In our case, we call that sample to answer, and also the cost. So we've gone from literally millions of dollars to get a human genome. A human genome is 120 gigabases of data, and we've now down at the $600 range, and we expect to be shipping $100 genome in the next few years. So the demand for sequencing data for life sciences applications, particularly for research now leading into clinical applications, is really driving the cost reduction and the time reduction, the time it takes to get that answer. And similarly, the innovations in the synthesis, we've seen big reductions in both the time and the cost to synthesize DNA for a variety of applications. So the life sciences industry is got a very healthy roadmap, a lot of competitors, and we fully expect to keep driving down both the cost and the time it takes to get the answers. And then your second question, Joe?
Yeah, my second part of that question was, how are the requirements for data storage different than those from the life sciences industry that you just described?
Sure.
Yeah.
So I think some important differences in requirements are that it really goes back to that coding step that Daniel described, where you can encode error correction. So in the case of life sciences, you want to know all the information. You want to have very high quality. You want to have very low error rates. So 1 in 1,000, 1 in 10,000 chance of having an error, but with no error correction capabilities built into the oligos. In the case of DNA data storage, then that can be intrinsic in how the data is structured, how the oligos are structured. So you can tolerate higher error rates, and with that, you can also see further improvements, both that could be in terms of run times, in terms of the cost per genome. So I think there's some unique opportunities with the DNA data storage application to further optimize both the time and the cost for both the synthesis and the sequencing steps to take advantage of that error correction that can be built in.
Great, thanks, Craig. So I'll switch over to the chat now, or pardon me, the Q&A, and there's a few questions here that we should address. How about maybe Karen, perhaps you can take the first one. How do we read data stored in DNA quickly and efficiently? At what rates can data be read from DNA today?
Right. In terms of rates, I think I'll defer to Craig on that. But essentially, there's two basic ways today to read the DNA, optical and electronic. Illumina, for example, uses the optical approach and can achieve quite high parallelism, which results in read throughput. The other option is electronic, so with nanopores and other companies working with sensing the DNA electronically. You can also up the parallelism there quite a bit by replicating the cells. So that's essentially how you would get to high throughputs. Craig, I don't know if you want to comment on the rates specifically.
Yeah, so just to throw out some numbers, for an Illumina instrument, so our highest throughput instrument, what's called the Novaseq, with the highest throughput flow cell, runs at 6 terabases, so effectively 6 terabytes of data in 44 hours. That is done in batch form. So we have this highly parallel process using what's called SBS. We load the DNA into this cartridge called flow cell, and then we measure 6 terabases in one run. That throughput is optimized to get us to the lowest cost per gigabase. You can run faster, but you will trade off the cost per gigabase.
Thanks, Karen. Thanks, Craig. So I'll move down through the list here of questions from the audience. There's a question around what are the main challenges in DNA as a commercially viable storage system? And what's the main technical issues of semiconductor nanopore technology? We don't really have any nanopore representatives here, but maybe Stefan, do you want to take a shot at the first question? What are the main challenges in DNA as a commercially viable storage technology?
Yeah, sure. I can make some general comments, and then the other panelists can add to that. It ranges from the cost, basically, of the synthesis to the methods to storing data. Right today, we have a process, for example, that allows us to store the data in a capsule for a very long time. Right, there may be other means to store the information, as well as the reading, the cost of the reading. Right, and the full automation process, right? Those are certainly areas and opportunities. And then, of course, as was indicated in some of the other comments, the whole opportunity to have very powerful encoders, right? And the interchangeability of all of that. And all of these aspects are being discussed within the DNA Data Storage Alliance, because we know that if we don't build an ecosystem that allows for that interchangeability and that has an opportunity for cost-effective solutions, DNA data storage will not take off at a large scale, which we're all hoping for.
Thanks, Stefan. Yeah, if anyone else wants to chime in, I think we've covered that topic pretty soundly. Looking through the chat, there's a few more questions about nanopore arrays, and I really don't know that we're the best group to talk about that, but there is a question about the industry consensus on best approaches for read. Does anyone feel that we're approaching that, or if there is a consensus? It seems like, yeah, that's still an open question, but if anyone would like to comment.
I mean, I'll make a comment that there's a variety of different read technologies. Illumina is using SBS. There's companies such as PacBio that are also using an optical approach, and then there's the sort of solid state approaches by the like of Oxford Nanopore Technology and Iron Torn from Thermo Fisher. So depending on the application, depending on exactly the type of data you're wanting to read, whether it's short or longer lengths of DNA, then you'll pick a different sequencing technologies. I think there's pros and cons as ever of all those approaches. And today, for example, Illumina, we're focused on SBS, and that certainly is a large portion of the total amount of DNA sequencing data that's generated each year is generated on SBS platforms today.
Great, thanks, Craig. So I'll move on in the questions. There's a a question about the hardware. And the question is, what type of physical media is used to store and retrieve DNA data, and what interface exists to allow for reading this data with more traditional computer systems? I think we've talked a lot about the sequencing hardware that's being used. Daniel, maybe you could talk a little bit about the hardware that's used on the synthesis side, and then maybe Karen, you can talk about the interfaces to the more traditional computer systems. But go ahead.
Yeah, sure. I'd be happy to take that one, and it connects to actually the third part of the previous question, that the opportunities for the cooperation of DNA field and semiconductor technology field. So just a comment on that one. The semiconductor field is super crucial for the success of DNA storage. If you see the presentation from Twist or from Illumina, at the base, at the core, we're dealing with semiconductors, trying to miniaturize and lower the cost using the advancements in the semiconductor field. So they're very, very tied together. And it also relates to how to store the media. But the media here in DNA is the DNA itself. This is an important concept that is not familiar in the current storage world. In the current storage world, we get a media from the factory. It can be a film for tape, or it can be a hard drive with the magnetic plates, but it comes empty, and then we write the data on top of it. The way it works in DNA is that the medium is the data, and the data is the medium, we used to say, which is once the DNA comes out of the factory, it already contains the data on it, because the DNA represents the data. What we use today, Twist is using one solution, as I said, from imaging. Again, you can hear the presentation about this technology. Some others use other technologies, but we need to find technologies, and we need to work on technologies that is storing the DNA for the longer time. As we said, in order to store it for the long time, we need this special technology that we want to keep it to consume as less energy as possible. Because we're talking about archiving data for hundreds or thousands of years. And we need to develop a way to access the data that is stored in this technology in an efficient way. So the current physical media that we use, or the container, as I described before, is that capsule that puts the DNA in the right condition without water, without humidity or harmful gases to the DNA. But it is used to be stored like that and not open. Once we open it, we kind of need to put it again in a capsule. So we need to develop new kind of containers also that will be able to allow readability and access in an efficient way.
Great, thanks, Daniel. Karen, do you want to take the second half of the question about the interfaces that exist to allow reading of the data with more traditional computer systems?
Yeah, so ultimately, both the encoding and the decoding processes are fully digital. The output of the encoding process is essentially the sequences of ATCs and Gs, and in what sequence to produce them through the synthesis process, which is effectively what the actual writing, the physical writing of the medium is. And then on the other side, after sequencing, what we get is essentially a number of different reads, which are, again, electronic encodings of what the molecules observed by the instrument that read them. And so that is, again, electronic signal that needs to be translated into the bits that we originally wanted to store, and additional error correction. So all this is really done on the electronic side of things, not necessarily on the molecular side.
Just to add, John, I see the second part of the question with what interface exists to allow for reading this data. I'm not sure that we will get to a place where everyone will have a DNA writer and reader on their computer, on their desktop. The machines today and how it works, it's a bit more complicated. And the way, at least we see it at Twist, is that in the beginning, the DNA storage technology will be behind the scenes for a lot of people. Like, it will be in a data center. That in this data center, we'll have another big box over there that will be able to connect with a usual interface, like an Ethernet cable or optical cable that connects to the data center. But inside the box, there will be a lot of technology, but from the outside, it will look just like it as another component in the data center. I'm not sure we will see it so soon in traditional computer systems or at the consumer level.
Yeah, thanks a lot, Daniel. That's a good question, or follow-up, pardon me. Another question that's come in that I came to a point that you made during your introduction is a question about standardization. And the question is, would it make sense to standardize the encoding or the error control? And maybe to expand on that question more broadly, like at what point do you think standardization becomes important or rate limiting? Yeah, Daniel, if you want to start with that, but if others have comments, it'd be great to hear them.
Yeah, I'd be happy to start. So I think a lot of the audience here have been through different storage media and solutions. Some of them were good, some of them didn't execute as well. And what we see from history is that the ones that were standardized broadly made a huge success and stayed with us. We can look at USB for an example. This is a great example of a standard that was made to connect all the systems and all the companies in a kind of a similar interface. And this allows us to take a computer from one company and plug a device from another company. We plug it in and it works like magic. And this is the power of a standard, that it allows this ecosystem to flourish because we have a standard and everyone knows what they need to do in order to be able to talk to each other. We see that with LTO and how it helped tape to gain traction and success in the past few years, and how important it was to develop the LTO standard. And I think it's the same with DNA data storage. In the birth of a new technology, a lot of customers have questions, and we need to create trust. And standards help to create trust between the customer and the companies, because the customer know that they buy DNA from one company, they can read it with another company, and they can store it with a third company, and their data will never be lost because there is a standard on how the data was encoded and stored in the data center.
Yeah, to complement that, yeah, certainly having agreed formats, both physical for how you store the DNA and logical for how the information is laid out on the DNA is helpful. Something that as probably most of the audience knows, is we need to be careful with what we standardize so that we don't sort of stifle innovation in different areas, and so that's an important but delicate piece that needs to be carefully thought through.
Yeah, and just to add, I think the use by using natural bases, I think that's also important because you've got that sort of inbuilt long-term accessibility to the data. We'll always be wanting to read natural DNA for health reasons, right? For clinical practice, so that capability will exist. So if you encode a natural basis, you'll be able to sequence it back. I think the other point that's also important to get for standardization, to really have the long-term benefits, which is an archival advantages, is the storage conditions to ensure that the data is robust, and that over a period of decades, that the data, if kept in those conditions, you don't need to check the data. It will be, you can guarantee that it's going to be intact decades later, hundreds of years later, and that'll really help with the value proposition for this.
Yeah, thanks everyone for contributing to that answer, and that leads into the next question that I'm seeing in the chat, and this is a question about redundancy and reliability of the media. We talked, and just Craig's answered, there's hundreds of thousands of years, perhaps longer in the wild, as Karen mentioned earlier. So the question this panelist or this attendee asks is, how much redundancy is built into the technology? Karen, do you want to start with that, or does someone else want to start?
Sure, I can start, and I'm sure folks will complement. One of the beauties of DNA is when you make the DNA, you already make many copies of the same piece of information. So you get some natural replicas by the nature of the writing process. In addition to that, as I think Stefan mentioned earlier, DNA is pretty easy to copy. And so you can increase that redundancy sort of in a pretty straightforward and standardized way. And in addition to that, on top of the physical redundancy, which we call these multiple molecules representing the same piece of data, you could add, the regular error correction that we're used to in the storage world. So you add some redundancy based on mathematical codes. And when it's time to recover the data, you can use those mathematical codes to fill in, spots that are missing or errors that creep in through the process. So quite a bit of room there, but also quite a bit of room there to develop new codes, but also quite a bit of natural redundancy that we get from the processes that normally manipulate DNA.
Great, thanks, Karen. If there's no other additions, then I'll move to the last question that's in the Q&A. And this has to do with the graphic that we've been displaying here for a while. And the attendee asks, I've seen this figure and method presented many times. Is it the only viable method for DNA data storage? Are there notable alternatives you can speak about? I don't know if Craig or Stefan, if either of you want to start this one.
I don't have anything to add. I mean, this is a fairly well understood series of steps, and I think the focus has been on getting some of the roadblocks which we've covered. Certainly, there's different ways to do synthesis, and there's different ways to do sequencing. So I think that's where maybe the uniqueness of any application comes. I know, Stefan, have you got anything to add on all the ways?
Yeah. We attempted here to basically describe the process, right, at a very high abstracted level. To Craig's point, how you ultimately encode and how do you synthesize, right, how you represent information. There are multiple different ways, right, that that this is done, as well as we talked about when you look at the retrieval, right, the methods to reading DNA. There are multiple methods, right. This graphic is intended to bucketize it, if you want, so at the very high level, so people have an understanding how the digital data turns into DNA and DNA turns back into digital data. That's the purpose of the slide.
Yeah, maybe I'll just add one more comment, and it's really about the maximum interoperability as well with this. There may be other approaches that are more sort of closed box, where the synthesis and the sequencing are tightly coupled. But if you want a sort of maximally interoperable, particularly over decades, then I think having these distinct steps is sort of certainly optimized towards that.
To complement, so there are different ways of do this encoding that don't necessarily, follow in the details this general pipeline, but the pipeline, you need to translate bits to bases in some way, and you need to have a way to store those bases and create the sequences of DNA. You need to store it, you need to retrieve it, you need to sequence, you need to decode it, right? So it may not be exactly in the way we describe, but meaning, short sequences, for example, and particular details, but generally, that sort of the way that we envision it. We should explore all sorts of approaches. I think the jury's still out. I think there's quite a bit, to explore and to develop when it comes to DNA data storage. So, certainly we have a view that's the most common among multiple companies, but I think we need to embrace every view until we get to a system that's working at the scale that we can use for archival DNA data storage. So it's still early, but I'm excited about it.
Yeah, great. Thanks everybody for your responses. It looks like we're at the end of the session. So at this point, I'd like to thank the panelists for engaging in this discussion. And again, thanks Nia for providing the forum. Cheers, thanks again.
Thank you. Feel free to ask questions in Slack and we can still answer those.
Yeah, thanks, Dan.
Thank you.
Thank you.